Okay, everybody. So here we have the eigenvalues and eigenvectors of a linear transformation. This is the last part on our series for 7.1. Well, I just want to say that this is kind of the same thing we've been doing for the entire 7.1. We're just kind of looking at a different way because a linear transformation, as you know, is t of x equals ax. That's a linear transformation. And we know that eigenvalues is when you have ax equals lambda x. So we're just going to sort of cut out the middleman and say that t of x. So if t is a linear transformation, and you have a vector where the result of where the transformation of t on that vector gives me lambda times the original vector, then that vector is called an eigenvector. And if you look at all the eigenvectors, that correspond to a particular lambda, that's going to be the eigen space. Just so really, this is really literally the exact same thing we've been doing before today. It's just that now I'm sort of giving it a different name in a way, or just showing how what we did with t of x equals ax also applies if I just go straight and say t of x equals lambda x, kind of the same thing. So for example, if I have a linear transformation from R3 to R3, and the matrix relative to the standard basis is this, that's our standard basis, of course, and in example 5 in 6.4, we found the matrix T relative to the basis, to a different basis, is this diagonal matrix. So our question is, for a given linear transformation, can you find a basis B prime whose corresponding matrix is diagonal? And that's really what we want to do here. And we're going to do kind of the same thing we did back then. We're going to look at lambda I minus a, which gives us this determinant right here, which if you multiply that all out, comes out to lambda minus 4 times lambda plus 2 squared, because the eigenvalues then are positive 4 and negative 2. The bases for the eigenspaces are going to be B1 equals 1, 1, 0, and B2 equals 1, negative 1, 0, 0, 0, 1, respectively. And this is something you can verify by just doing the same process we've been doing until now. And there you go. But you see that these guys here are the eigenvalues. These guys in here are the eigenvectors. That's really all I wanted to talk about. I just want to show that, I guess the main point of this very, very brief little video is just to show that the idea of eigenvalues and eigenvectors of a matrix, you could talk about the eigenvalue or eigenvector of a linear transformation, particularly because a linear transformation is a matrix times a vector, or a vector times a matrix is a linear, whatever, you get my point. So works both ways, actually. So that, my friends, is the story. That's the end of 7.1. We will get to 7.2 in the next video. See you there. Bye, everybody.